Okay, today's lecture, much review, um, and I hope you will find it familiar, old friends. Start with the ratio of current, of voltage to current, which you remember is the definition of resistance. You had Ohm's law, which said that voltage was proportional to current, but then that constant of proportionality we call resistance, capital R. The units of resistance are ohms, with that wonderful onomatopoeic poetic symbol, the omega for the ohm, and it's equal to a volt divided by an amp. And you recall from last year that resistance does not depend upon voltage. It does not depend upon current. It only depends upon that medium that the current is flowing through. That we had a mnemonic, which we may or may not have made our own last year, and maybe you have a better one, and if you do, please share it with all of us. But here is for resistance and things getting hot, and you have little e's in there for electrons flowing in the current. What could be more meaningful? So it depends upon, and with the chorus answer we all say, the material that is flowing through, and the length of that material, and the temperature of that material, and the diameter of that material. We then introduce this quantity rho, an R, because it's with resistance again, but it's not resistance, it's resistivity. And this is a measure of the material's contribution to the resistance. Resistivity is measured in ohm meters, ohms times meters, and it is the resistance of the material instead of the resistance of an object. If you have a particular wire, it might have a particular resistance, and that same wire, if it were longer, would have a different resistance. But the copper making up the wire has a resistivity. And so this speaks to the properties of copper, not a particular construction made with the copper. Having introduced this idea of resistivity, we finally have this equation describing resistance, which depends upon the material and the length of the material, and up here we use the D, but it's an A. You could also say malt if that works for you, but malt lacks the ease or the sense of heat. But if malt works better, then there you go. The cross-sectional area of the material, that if you make the wire of a different material, it will have a different resistance. If you make it twice as long, it will have twice the resistance. If you make it twice the cross-sectional area, it will have 1/2 the resistance. Okay. And we're going to talk temperature is not here, and I'll show you in the next slide how temperature comes in. But first, the book goes on, not having confused you enough, to take this familiar formula, which we call Ohm's law, and then it's going to replace the resistance with that equivalent equation using resistivity, and then it takes this equation and divides through by L. I've also regrouped over here to put I over A times the rho. So the L comes over under the V, the A comes under the I, and then we have a rho that we're multiplying by. Well, all of these have names. Voltage, between the two ends, there's a certain potential difference V. If you were to divide that by the length of this, voltage and distance gets you to electric field. That this would have a uniform electric field inside of it if there was a current flowing. You say, whoa, wait a minute, Mr. Houghton, that could be a conductor, and conductors have no field inside of them. Ah, says Mr. Houghton, that's only for stationary charge. But if you have moving charge, if you have a current flowing, then you will have a field inside of a conductor, and it will be a uniform field. So it is indeed the case that E, the strength of this field in here, times the length would be equal to the potential difference between the ends. And this quantity, current divided by cross-section area, is represented by a J, and we call it the current density. Well, this equation here corresponds to this equation up here. You have the kind of the voltage term and the current term and the resistance term. And according to the book, this equation here represents the microscopic, the fundamental electrical behavior in an electrical circuit. This is more of the macroscopic behavior that's going on, the very gross behavior, but at the electron level, this represents much more what is happening inside of the material. You will have problems dealing with this, but basically they will be just plug and chug. You need to master the definitions of current density and resistivity, but there you are. There is another unit called conductivity, and that is more just a joke, but it's the reciprocal of resistivity. This is how difficult it is for current to move through. This is how easy it is for current to move through. And then there's a little physics joke that, and it's for real, but still I think it must be a joke, that if the units of resistivity are ohm meters, then the units of conductivity are mho inverse meters. And you can see what they've done here. Aren't they cute? Okay, we move on before we gag. Here is a table from your book showing the resistivities, not resistance, resistivities of some materials at room temperature, which they say is 20. I thought room temperature was 25, but I guess they're saving heat. Here's the resistivity in units of ohm meters, and you have some metals. Silver having a lower resistivity than copper, and both of them lower than gold. Why would you make electronic components out of gold if it's got more resistivity than silver and copper and it costs so much more? Well, we'll talk about that in class. You put down your ideas on your worksheet. Then you have these things called semiconductors. This is 10 to the minus 8. Here we are at 10 to the 3, 10 to the minus 4. So they're someplace in between. And then some insulators. They only have 2 for you. 10 to the 14, 10 to the 16, way up there for the resistivity. Tremendous resistivities for those. But while we are here at this table, these are the values you'd substitute for rho, depending on what material they gave you in the problem. Look at this column here. The temperature coefficient of resistivity. This is where the T in melted comes in. That this is per inverse Kelvin. And what they are saying is the resistivity of copper. They haven't told you for silver. 1, 2, 3, 4. No, they've told you for everybody. Okay, so here's silver. And what this means is for every degree Kelvin that you go up, it's an inverse Kelvin. For every degree that you go up Kelvin, which would be the same size as going up 1 degree Celsius, the resistivity is going to go up by this amount. So if you went up 100 degrees, then instead of this being, well, let's make it easier on ourselves. That's that 2 there, minus 6. So I would have to go up 1,000. If I went up 1,000 degrees, I think I'm doing this right, then the resistivity would go up 1,000 times. No. At any rate, Mr. Houghton is confused. For every degree you go up, this would increase by this amount. Yeah, we better get that straight before we have to work with it. And it would increase by that amount for every degree above 20, and it would decrease by that amount for every degree below 20. Okay, while we're here, notice for the semiconductors, it has a negative. So as normal materials get hotter, their resistance goes up. But as semiconductors get hotter, their resistance goes down. Pretty weird, huh? I'll say. Okay, you have a checkpoint just going at the effect of the length and the cross-sectional area on the resistance. These are all the same material, so they all have the same rho, and they're all at the same temperature. So you go ahead and do that checkpoint. And here is the cutesiness for today. This is from edition 6. And I don't know why they don't include this essay in every one. But this had to do with the Hindenburg, not because it bumped into this tower, but because it was moored to the ground. They had ropes tying it to the ground, and that is what led to a spark which caused the Hindenburg to explode. And the Zeppelins had been around for quite a while without these catastrophes, but the Hindenburg had a new coating that was painted on the outside that was thermite. It was an aluminum compound, and Mythbusters, I think, would like you to believe that it was the thermite that caused this great fire, but it really wasn't. It was the fact that the thermite was resistive. Oh yeah? So what's so important about that? Well, let's get into it. Oops, no we can't. You have to just listen to me talk. The problem was there was a rainstorm, and so these ropes that were holding the Hindenburg to the ground were wet. And that made them conductive. And the ropes went up, and then they attached to metal connections that went to a skeleton, a metal skeleton inside of the Hindenburg. They probably passed through the skin, that this metal skeleton went through the skin as well. But because the skin had been made insulative, where the metal hooks went through the skin, where the ropes came up and touched, was not a conductive pathway. So the metal skin came to be at the same potential as the ground. But the rest of the skin of the Zeppelin was at the potential of the air at that height, and it was unable to become an equipotential because this was not conductive material. Well, the Earth's electric field varies, I think it ranges somewhat, but 150 volts per meter is not an atypical value for the Earth's electric field strength. And this was about 43 meters up in the air, which means that at the ground there was one electric potential, and at the air up where the Hindenburg was, the potential was 6,450 volts or something like that. So you had the metal skeleton at one potential and the skin 6,000 volts different. And that was a large enough difference in potential to cause the hydrogen between the skin and that metal to break down, become ionic, and an electric spark jumped through the hydrogen, and that spark is what ignited the hydrogen. I hope you followed that, because that was hard for me to create, and it is very cool physics. If you didn't get it, you were just witness to something very cool. On to new topic. Ohm's law. Ah yes, that the potential difference is proportional to the current that flows. But you may recall from last year that it is only a law if you obey it. If you don't obey it, then it's not the law for you. Here is a material that obeys Ohm's law. You can see the current on the vertical axis being proportional to the voltage on the horizontal axis. But here is a material that does not obey Ohm's law. That as you increase the voltage, the current does not respond proportionately. These kinds of materials that do not obey Ohm's law are called semiconductors. And I probably pointed this out to you last year, but I point out to you again that this event here is a semiconductor turning on. If you put enough potential difference across the semiconductor, it suddenly becomes conductive. It changes from an insulator, where no current flows, to a conductor, and you have current flowing. That's a semiconductor turning on. It is an electric switch that you can control simply by changing the potential across it. And that's how all of your semiconductor devices, including your computers, work. Please do not lose track of the fact that V equals IR, which is not Ohm's law, but we keep calling it Ohm's law. That is true for all materials. For that here, if you were to take this potential of 3 volts and this current of 1.5 amps and divide the current into the voltage, you would get what the resistance of the semiconductor is. So V equals IR is true for everybody. But V is proportional to I is only true for what we call ohmic devices. New topic! So, a small infinitesimal of charge, dq, moves through a voltage drop, V, in a time dt. If we look at the change in potential energy, voltage, potential energy, potential energy. Ah yes. Voltage was the U per charge moved, right? So if it's a small little infinitesimal charge dq, then you get a little infinitesimal of energy du. And then I'm going to take this equation and divide it by dt. And I have this quantity is equal to V dq dt. But of course dq dt is I, the current. What is du dt? What is the rate of change in potential energy, or the rate of change in energy? It is indeed power. And so you have this equation, which you recall from last year for electric circuits, that power is equal to voltage times current. Please be aware that there are several other forms of this equation for voltage, that if I replace V by IR from that which we mistakenly call Ohm's law, you get this expression for power. And if you replace I by V over R, you get this expression for power. But these two would only work for ohmic devices, where the current and the voltage were proportional. It does not work for semiconductors. This works for semiconductors. These two do not. Thank you. That concludes the lecture.